tập câu này là
maybe next thing will be
Okay, let us begin. Okay. Last chapter. Very small. Magnetic effects of the issue is settled. So we will be starting the new chapter today. Magnetic effect of let us start. So first let us become. Let's revise quickly. What are the properties of a magnet? Okay, what are the properties of a magnet? We'll come to magnetic effect of a current. We'll come to magnetic effect of current little later. First, let us understand what is the property of a magnet. You are familiar with magnets. What are the properties of the magnet? Two important properties. It has attractive property. What is attractive property? It attracts pieces of iron. Attracts small pieces of iron. This is one. What is the other property? What? That is about like poles repel, unlike poles attract. So, okay. Second property is like poles repel, unlike poles attract. Okay. What is this NNS? North and south. Okay. What is the third property? Magnetic field. That will come to it. What is the third property? Does it have directive property? The third property is it has directive property. What is directive property? So when the magnet is suspended, it always points in geographic north, right? So when magnet is suspended, it always points towards geographic north. Okay. So not only attracts small pieces of iron, it also attracts nickel and cobalt. Okay. So it has two poles, north and south. Okay. So these are important properties. Okay. Now, there's something called as magnetic field. Now, what is magnetic field? So it is the region of influence around the magnet in which any other magnetic substance, okay, experiences a force. What did I say? It is the region of influence around the magnet in which any other magnetic substance experiences a force. What force? Magnetic force. Okay. So it is region around magnet where any other magnetic substance experiences or magnetic force. Okay. So this could be magnetic force of attraction or repulsion, depending upon repulsion. So this force is greater near the magnet. As the distance increases from the magnet, this force reduces drastically. Okay. And just click here. Okay. So magnetic field or the magnetic force, this force is stronger near the magnet and at far. Okay. So if the distance from the magnet increases, this force also becomes weak. Right? So this is the basic, and every magnet will always have two poles, which means if you break this magnet into two parts, right? So let us say I break this magnet into two parts. So I can break the magnet along its length, or I can break it like this. So it will make two small magnets like this, each having north and south poles. Again, if I break it vertically, then too it will have two poles, north and south. So a magnet is always a dipole. It will have two poles. Okay? So you cut it either along its length or midway. It will always be a smaller magnet. Now let us see how to represent the magnetic field. Right. So magnetic field is represented by magnetic field lines. Okay, let's see how to draw the magnetic field lines. Can I erase this side? The magnetic field strength or magnetic field of a magnet is represented by magnetic field lines. Okay. So there are some rules. What are the rules? Rule is the magnetic field line comes out of the North Pole and enters in the South Pole, like this. And completes the loop from south to north. This is how the magnetic field line is formed. It is always a closed loop. Okay. It emerges from the North Pole and enters at the South Pole. Okay. Here, like this. So actually, what you're saying here is somewhere it is concentrated, but it is equally spaced. Okay, it is uniform. The field lines are equally spaced. It's not like it is constricted in the middle. So these lines are separate lines. Okay, they are not intersecting each other. They are separate lines. See the diagram in the book. Book में तो दिखाई नहीं रहा है. So these lines are straight lines. Okay, they are not intersecting. In the NCERT book, they are not both. So what is uniform field? What is uniform field lines? Parallel lines equidistant from each other. So these field lines are uniform actually. They're all equidistant. Non-uniform is this is non-uniform. The spacing between the lines are not even. They are closer near the magnet. As they go away, it is spreading out. So this is non-uniform. Okay. How the strength of the field is decided? The non-uniform field could be something like this. They are not parallel to each other. Okay, here it is closer, but now the space is increasing. This is non-uniform. Now, where the magnetic field strength is more, wherever the number of lines are more. Okay, so the magnetic field strength is. Now, let us discuss the properties of magnetic field line. Properties of what are the properties of magnetic field lines? Magnetic field strength is stronger in the region where field lines are crowded. Okay, wherever the field lines are crowded, the magnetic field is stronger, and vice versa. So you can see that near the poles, the field lines are crowded. The field strength is maximum near the poles. Now, if you look here, the field lines are spread apart. So here the field strength is not as strong as it is near the poles. Okay, so you have weak field perpendicular to the magnet, right? Second, it is a vector quantity. So it has well-defined magnitude and direction at every point in the region around magnet. Magnetic field is a vector quantity. Thus, has magnitude and direction. Okay. As unit point. Okay. So magnetic field is a vector quantity and it has a unique magnitude and direction at every point around the magnet. So tell me, will the magnitude same at these points A and B? Huh? Magnetic field strength is expressed as Tesla. Tesla is the unit of magnetic field strength. Tesla सुना है? वही है. So the field direction is along the tangent. At any point on the field, the direction is along the tangent. What is the direction? Along the tangent on the magnetic field line. So the direction of field magnetic field at any point on the field line along the tangent at that point. Going from to south. Again, so magnetic field is a vector quantity, thus has unique magnitude and direction at every point around the magnet. How do you get the direction? The direction of magnetic field at any point on the field line is along the tangent at that point. Going from north pole to south pole. The direction is always from north to south. So obviously the direction here is somewhere else, here it is different. Unless the direction changes, the loop will be not found. क्या हुआ? कुछ नहीं हुआ. So the direction of magnetic field at every point is along the tangent. Okay, so keep this in mind. Then third point is magnetic field forms closed loops, right? Fourth point, magnetic field lines form closed loops. And is it emerges from North Pole. Okay, it emerges from North Pole and merges into South Pole. Outside the magnet. From outside the magnet, whereas from South Pole to North Pole inside the magnet. Okay. We're almost done. And the last property is two magnetic field lines do not intersect each other. We are reaching that. Oh, third. I missed third. This is third. There may be different numbers in the book. The magnetic field lines or the magnetic field lines so I'll now erase it. Never intersect each other. Never intersect each other. Why? अरे ये क्या हो गया? हाँ. From fourth I wrote directly to. Okay. Now this is fine. So this you can self-correct. Okay. Now why so? Because two directions. At the point of intersection. So let us say the field lines were going in this direction. So at the point of intersection, there will be two tangents possible. But what did we say? It is a vector quantity, and therefore it has to have a unique direction. Then only it is a vector quantity. But at the point of intersection, एक इसको यहाँ पे भी tangent possible है, एक यहाँ पे भी possible. So this is not allowed. Okay, it's not allowed. That's why it will never intersect. So it will be very close to each other, but will never intersect. Okay. So outside the magnetic field is non-uniform. Inside the magnet, it is uniform, parallel, equal spaced. Is that clear? So now with this thing in mind, you will be able to answer most of the queries. Mostly this is the play, right? So तुम मुझे बताओ. If I keep a magnet here, how do I draw the magnetic field lines? How do I know that these are the magnetic field lines? I'll use another magnet, correct? Let's say if I keep a bar magnet here. So bar magnet also is a magnet only, correct? So the arrow, the north pole will be repelled by this north pole. So it will point in certain direction. So you mark that point. So in the lab, this is how you will draw the magnetic field lines. Now you lift this and place it on this point. Then wherever it points, just keep pointing the dots. And you will see that when you join them, it makes like this. Okay. Now let us say you have a magnet, and on top of magnet you have kept a glass plate. So then you will see that this is how the arrow points. Understood? Understood how to draw the magnetic field line? Last paper. How is it? Let's say this is the magnet. Magnetic compass ही है और ये बार magnet है. lab में you will have the experiment to draw the magnetic field lines. So how will you do? You take a chart paper, right? You place a magnet over here. Then place a bar magnet. You will see that the bar magnet will be repelled by the magnetic field. So when you join all the dots, you will see that it makes a closed loop. Now change the position. You will have another line. So wherever you keep changing the position, you will have so many lines above and below. What I'm saying is, but you can't insert the compass into the magnet. Na? So the chart paper is just one of the plane. Magnetic field line is in 360 degree space. It is also from here to here. It was also from here to here. Okay, everywhere. So now, if you keep a glass plate over here, then what it will show? It will show that now the compass is kept above. It will go like this. Understood? So that's why. And if it is coming from here, it has to close the loop. That clear? This is what it is. Right. In case of bar magnet, this is not very clear, but we will learn something called a solenoid. Very soon we are going to go there. And that is an electromagnet. What is this? This is the permanent magnet. Right. So, do you have any questions on this? Read the notes given in the volume. In case I've missed anything. So, like if you keep a magnetic compass here, कहाँ पे हुआ direction? If you keep the magnetic compass here, the tangent and the direction of magnetic compass will be like this. Because magnetic compass is also a small magnet. So here, like poles will repel. So magnetic compass में क्या होता है? ये वाला जो pole है, this is north, this is south. The tail is south. So arrow is north, so north will be repelled. ऐसे करके वो south की तरफ चला जाता है. Is it clear? All poles are of equal strength. Right? ठीक है? So we have covered everything. Now let's go ahead. Now, Oersted's experiment. What is the magnetic effect of current now? So this is where the chapter begins. This is revision. Apart from the properties of the magnetic field lines, most of it you already know. Okay? So only thing is like the vector consideration and they cannot intersect. This is the only new thing here. Right? Now it is observed. This chapter is totally an experimental chapter. Very minimal or almost no numerical, but some laws are there. Okay. So whenever the current is flowing through a wire, okay, when you keep a magnetic compass near it, it shows deflection. Right? So what does this tell you? Like, let us say there is a circuit, okay, there is no current flowing in it. And let's say there is some plane where you have kept a magnetic compass, right? So when the current is not flowing through it, that time, what is the default direction of the magnetic compass? North, south. Okay. But now when you blow current in the wire, it deflects. So why the deflection is taking place? It has got something to do with the flow of current. That means the flow of current is producing or generating its own magnetic field. Right? Only then this compass will be deflected, and which is stronger than the Earth's magnetic field. Earth is also a giant magnet, but its magnetic field is very small, but enough to deflect the magnetic compass, which always points towards the geographic north, which is actually magnetic south of Earth. Understood? That's why the north pole of the magnet points towards geographic north. So that is actually magnetic south of Earth, right? And that field is weak. So when current flows, it produces stronger magnetic field. Likewise, when the compass is kept near a magnet, then this direction changes. Otherwise, if you take the magnet away, it will point in north-south. Let us say this is Earth's north-south, east-west. So if this magnet was not kept near the compass, it will point in this direction. Okay, but since the magnet was brought closer, it repelled it. That's how it pointed like this. Is that clear? So we said I told you, right, when I was describing magnetic field. What is the magnetic field? When any other stuff is kept, any magnetic substance is kept in the magnetic field, it will experience a magnetic force. And how that magnetic force acts? Like pole repel, unlike pole attracts. So here it is repelling this other magnet, small magnet, and that's why it is getting aligned parallel. Okay? And how it will repel? It will repel in its direction, in its own direction. So magnetic field is changing direction, and that's how the compass is following the magnetic field direction. Is that clear? So if the magnetic field is going like this, that means this side must be north, this side must be south. So for magnetic compass, it is the north of magnetic compass, this is the south. So south will be towards north of this magnet, and north will be towards south of this magnet. Is that clear? Okay, the attraction repulsion is acting at all places, which is why the magnetic compass is getting deflected. Okay. Now, our actual chapter starts now. So let's see what is Overstead's observation. What is Overstead's experiment? So Overstead experiment is this. So let us say you have some conductor. Okay. So AB is some kind of conductor, right? And when the key is closed, so what is the direction of flow of current in this? What is the direction of flow of current? So it will be B to A. Current will flow B to A, right? How much current is flowing? The ammeter will record for you. Now, if we keep a magnetic compass over here, right? Let us say initially the key was open. So where will magnetic compass point? It will point in this direction. right? When the key was open. Now when the key is closed, it shows deflection. Not only it shows deflection, when I keep the magnetic compass at different points, okay, and when I join the dots, I get a magnetic field like this. Okay, I get the magnetic field lines this. And as I go away from the wire, the distance between the magnetic field lines increases. Experimentally, I get this. So what does it tell me? Huh? You want to? Nothing is visible. इसमें देख नहीं रहे लेकिन तुम ही लोग देख रहे हो. Okay, so experimentally, what does this tell you then? It tells that the magnetic field is stronger near the conductor. This AB is also some conductor, okay? So field is stronger near the conductor. As you go away from the conductor, the field is weak. Because the field lines are crowded near the conductor. Okay, so this is Oersted's observation. What is the other observation? If we change the direction of current, then the direction of field also changes. Right? So two things are observed. A current carrying conductor produces concentric magnetic field lines around it. ठीक है? A straight current carrying conductor produces concentric magnetic field around it. Okay, the field lines are crowded near the conductor. Okay, field lines are crowded near the conductor and spreads out big spelling. How you corrected? What you corrected yourself? Spreads out at a greater or at a distance away from. Now it is written wrong. Doesn't do you understand the physics behind it? That's more important. Get out of that language mode. Grasp the concept. So what did I explain? When Oersted conducted this experiment, the magnetic field lines are concentric okay, crowded near the wire, and they get spread out as you go away from it, right? Instead of magnetic compass, you can observe these field lines when thin metal powder was spread. Okay, when thin metal powder was, iron powder was spread, and gently tap the plate after passing the current. Then also those iron powder will arrange itself into concentric circles, right? So the diagram is more clear in the book. So there are two ways in which you can experience this. So what I'm writing here is the observations of this experiment. Observation. What is the other observation? When the direction of current is reversed, the magnetic field direction also is reversed. If the direction of current is reversed, the magnetic field direction is also reversed. So therefore, we have made a rule for it. Otherwise, it becomes very difficult to remember what is the direction. So the direction is given by what is called as right hand thumb rule. Okay. So let's see what is right hand thumb rule. The direction of the magnetic field produced by right hand thumb rule. Okay. Direction of the magnetic field produced around the current carrying wire is given by right hand thumb rule. So what is right hand thumb rule? So stop writing, understand this first. So let us say the current is going up. Okay. So align your thumb in the direction of current and grip the finger around the wire. So wire should be in between. Okay. So the finger should be curled around the wire. So then this is the direction of magnetic field. Correct? You see here now. So what is the finger pointing at? Anti-clockwise direction. So when the current is upward, the field direction is anti-clockwise. And how is the speed? It is in the plane perpendicular to the current. Where is the field? If this is the wire, current is going up. Where is the field? In the plane perpendicular to the current. Is that clear? So field is like this. Okay. And how? As per right hand thumb rule. So now if the direction of the current is reversed, so now thumb goes down and now you get clockwise current. So finger has to curl around the wire. Clear? So this is what it is. So what is the right hand thumb rule? It states that what is right hand thumb rule? It states that when thumb of right hand, there is another right hand rule, so don't get confused with it. That is called right hand, Fleming's right hand rule. There is right hand also, but that is not in the syllabus. It is removed now. Pehle tha. It states that when thumb of the right hand is aligned along the direction of current. Which current? Conventional current. Always remember. Direction of conventional current. What is the direction of conventional current? High to low. Okay, outside the cells. Aligned along the direction of current. Then the field direction is from the direction along the curved dimension around the wire. यहाँ पे you have to include something. Around 8 के बाद में लिखो in a plane perpendicular to the wire. Around 8 के बाद में लिख लो in a plane perpendicular to the wire. Perpendicular to the wire. So this plane is perpendicular. Wire is coming out of it like this. Okay, wire is coming out of it. So this plane. The field is in this plane. Is that clear? So कैसे करोगे देखो? If you have a wire like this, ठीक है? What is the direction of field now? This is how it is. When you hold the wire, you grip the wire with your right hand. So the thumb is in the direction of current. And this finger will give you the direction of like this. Okay? So is the field clockwise or anti-clockwise? Anti-clockwise. And if the current direction is reversed, then it becomes clockwise. Okay. So now we will discuss this diagram. Right? So Oersted actually observed the magnetic effect in this circuit. तो उसमें क्या किया उसने? Listen everyone. ये जो मैग्नेटिक कंपास है ना, एक बार वायर के ऊपर रखा है और एक बार वायर के नीचे रखा है. ठीक है? So the above the wire, let us say, look here, these two diagrams. इसमें क्या हो रहा है? there are two diagrams. In one case, the magnetic compass is kept above the wire. और दूसरे में क्या किए? Below the wire. So field direction above the wire and below the wire is different, right? Let us say the current is coming towards me. So above the wire, the deflection will be in this side. Okay? And below the wire, the deflection will be on this side. देखो यही होगा ना, above the wire कैसे जाना है फील्ड? ऐसे. तो ऊपर ये साइड में और नीचे कैसे? ये साइड में. That's why the deflections are opposite in the diagram. Check the diagram. देखो deflection of the compass is opposite. Because above the wire, the direction is different than it is below the wire. Is that clear? और रूल वही है, नॉर्थ को रिपेल करेगा जिस तरफ, समझो फील्ड की डायरेक्शन ये है और तुम्हारा पॉइंटर ऐसे है, इट विल रिपेल नॉर्थ. ठीक है, जिस तरफ से फील्ड जा रही है वहां पे इट विल रिपेल द नॉर्थ पोल. ठीक है, सो विल गेट सम experience to, in figuring out the direction, and you get it right the first, on the very first day. This is a अब देखो यहाँ पे किधर जा रही है, ठीक है, यहाँ पे ऐसे आ रहा
I would say like